Good. Now we will start a new topic. It's called the Laplace transform. The Laplace transform. According to the Oppenheim's book, the definition of the Laplace transform is limited to, or initially it is limited to the so-called bilateral Laplace transform, which means two-sided. It's extending from minus infinity to plus infinity because, well, it's a good choice, by the way, because it does not require initial conditions and things like that, which you may remember from differential equations, because it's ranging from time is minus infinity. So there is no initial condition. We don't start from a place, we start from minus infinity and go all the way up to plus infinity. However, there is a problem that the majority of the literature that you may find in books, in other PDFs, other explanations, etc., you will mostly encounter the definitions of the so-called unilateral, single-sided Laplace transform, which we will also briefly mention about, but we will continue with the two-sided Laplace transform for the time being. And we are going to use this very nice property for the linear and time invariant systems, which is this: e to the sigma, I will say, which is a real number, plus j omega, which is an imaginary number. So in total, sigma plus j omega makes a complex number, times t. When it goes into an LTI system, okay, the output will be something which is related to whatever this sigma plus j omega is related to this complex number. Okay, it's in the form of an integral, by the way. And we know that if you take sigma is equal to 0, we have already done this. E to the j omega t goes in, and the output is h of j omega times e to the j omega t. But this time we have sigma plus j omega t. So this behavior, input-output behavior, if as well, not necessarily an imaginary exponential like e to the j omega. And it expands our degree of freedom by some magnitude. We are not limited to the frequency of omega only. Now we have also a real term in the exponent, which causes the signal to be a damping exponential like this, or a growing exponential like this. But when sigma is equal to 0, it's just an oscillation with no change in magnitude, because e to the j omega t, as we know, is just a complex sinusoid with no real damping factor of, or an exponential factor. But now we have a sigma, we may have a sigma, and we are going to denote this sigma plus j omega with a single complex value, which will be notated by s, as we already know from differential equations. So e to the st goes in, and the output is h of s times e to the st. And there will be, of course, a definition of h of s. H of s is like the Fourier transform. There's no difference in the formula, essentially. It's from minus infinity to infinity, h of t times e to the minus st dt. And when s is equal to j omega, when sigma is equal to 0, it means s is equal to j omega, then you have h of j omega, which is the Fourier transform. And it also gives you an idea why we are calling it h of j omega, right? Because we don't call it h of omega, but we call it h of j omega, because essentially it is h of s when s is equal to j omega, or when sigma is equal to 0. That's why we have a j omega concept over there, which was a little bit awkward. And of course, for signals, this is for the Laplace transform of the impulse response, which will be denoted as the transfer function. System transfer function. And for signals, the Laplace transform of a signal is, again, the same formula. X of s is equal to, from minus infinity to infinity, x of t e to the minus st dt. And Fourier transform is simple. It's just s is equal to j omega, where sigma is equal to 0 corresponds to the Fourier transform. Okay, as simple as that. So many of the results that we have obtained for the Fourier transform are also more or less available for the Laplace transform. In fact, more than that is available for the Laplace transform, because now here in Laplace transform, we have one more degree of freedom, which is sigma. We can play around with sigma in places where sometimes Fourier transforms are not possible to obtain. We don't have the Fourier transform, but by altering the value of sigma, we can have the Laplace transform. So sigma is equal to 0 is unavailable to you, but sigma is equal to some other number will enable us to develop the Laplace transform for some divergent signals, for example, where the Fourier transform does not exist. Now we will still have the Laplace transform. We may still have the Laplace transform. And we will, well, it may be a good idea to talk a little bit about the inverse Laplace transform, but I will come back to that point later, because right now let's think of the transformation itself. Let's see examples. From the examples, it will be a relief to you to find the answer, and it so much resembles the Fourier transform. It's even easier than the Fourier transform. X of t is equal to e to the at u of t. And we know that the Laplace transform inside the formula, let's put it it's from minus infinity to infinity, x of t, which is e to the minus at u of t, and e to the minus st dt. This is the integral that we need to evaluate. And because of this u of t, we now have the integral starting from 0, because for negative time, u of t is 0, therefore the integral does not contain any value. So the integration starts from 0 and goes to infinity. And we have a combination of e to the at and e to the minus at and e to the minus st, which can be combined, written as e to the a plus s t dt. And if we assume that the real parts of a plus s, the real part of a plus s is positive, so e to the minus a plus st is therefore a decaying exponential, if we can have it somehow, then this integral converges. It converges to 1 over s plus a, or a plus s. By the way, do you remember the Fourier transform? In the Fourier transform, we said that the Fourier transform is 1 over a plus j omega. So now we have 1 over a plus s. So quite similar to the answer that we have for the Fourier transform. And for the Fourier transform to exist, for the, let me write it in short, for the Fourier transform to exist, we had a greater than 0, a to be positive. Okay, that was our condition. But if suppose a is negative, which will be a growing exponential, e to the minus at u of t will be this time a growing exponential. Let's say a is equal to -1, then it would make e to the plus t, e to the t u of t, which is a growing exponential. And the Fourier transform does not exist. It violates the Dirichlet conditions. But for the Laplace transform to exist, we must have real part of a plus s to be greater than 0. And let's assume that a is already real. So a plus real part of s must be greater than 0, okay? Because real part of a is a. And we can write it like real part of s is greater than minus a. So if we can make sure that the real part of s is greater than minus a, the Laplace transform still exists. What was the real part of s, by the way? It was sigma. So sigma is greater than minus a. With this condition, even for negative a values, we can still have the Laplace transform. We can still think of or show a Laplace transform expression which is equal to 1 over a plus s. Now, how are we going to notate this sigma greater than minus a, or real part of s greater than minus a? We are going to notate or denote it on a so-called S-plane. So this is the S-plane that I'm talking about. Why am I putting it like a plane? Because S is a complex number, so it has a real part and an imaginary part. The real part I will indicate as the horizontal axis, and the imaginary part I will indicate as the vertical axis. Now, sigma is greater than minus a, or real part of S is greater than minus a, is something like this. Just give a value to a. Okay, a must be given to you, of course, in this question. For this question to be a valid, solid question, a has a value. Let's say that a is equal to 2. Okay. Let's write it in red color. Let's say a is equal to 2. Just a value. This condition here, sigma or real part of s greater than minus a, needs this kind of interpretation. Here we have we must have minus 2. Minus a is minus 2, so this is minus 1, and here let's say it is minus 2. Okay, this point is minus 2. So the real part of s must be greater than minus a from minus 2, in other words, will be notated with a dashed line here. We put a dashed line, and we shade the right-hand side of it. Okay, the right-hand side of that is the so-called place or the region where this integral converges. Hence, the terminology. The region's name, the name of the region is region of convergence. Convergence. Or ROC, region of convergence. Okay, this is the abbreviation that we have. We must indicate a region of convergence for this integral to converge. And this region of convergence must always be shown or indicated. You must always give the Laplace transform together with the region of convergence. So this, for example, as an answer is only partially enough. It's not enough. It's just a partial answer, and it will get partial credit, unfortunately. If it's 10 points, for example, and when I ask you what's the Laplace transform, you tell me 1 over s plus a is the Laplace transform. It's unfortunately only partially correct. you have to say this. The Laplace transform is x of s is equal to 1 over s plus a with a region of convergence, real part of s greater than minus a. You must always tell me this. You must tell me. Or you can show it on the S-plane like this. This is the region of convergence. So 1 over s plus a is the Laplace transform, and this plot is the region of convergence. Together with the two, it will be the correct answer. So there is an easy part of the Laplace transform because it's easier to write s as opposed to j omega. S is a Latin script, and j omega is partially Latin, partially Greek letter of omega. So the notation is a little bit more difficult. So the notation of Laplace transform is easier, but there's a price to pay, and that is the region of convergence. You have to always indicate. Soon we will see, or right now maybe, we will see an easy way to determine the region of convergence and its meanings. But before that, let's proceed a little bit with another region of convergence case, which corresponds to A is equal to, so this is another S-plane, or the same S-plane actually, for another A. And we have an imaginary part here. And let's assume that with a different color, blue, let's say this time, A is equal to minus 2. If A is equal to minus 2, by the way, e to the minus at will become e to the 2t u of t, which is a growing exponential, and the Fourier transform does not exist. That's a problem, mostly. So where is a minus a point? A is equal to 2 corresponds to minus a being 2, okay, like this point. And the region of convergence is real part of s greater than minus a, greater than 2, in other words. It's here, to the right side of 2. This is the region of convergence. Region of convergence. For the red one at the top, we had the region of convergence, which is a little bit larger, starting from minus 2 to the right. And we also know that if a is equal to 2, then the Fourier transform also exists, because e to the minus 2t u of t is a decaying exponential, and its Fourier transform is 1 over 2 plus j omega. Okay, that will be the Fourier transform. The Fourier transform exists for a is equal to 2, but for a is equal to minus 2, the Fourier transform does not exist. And where do we see it? By just looking at the region of convergences, it is possible to make this kind of a deduction. For one of them, the Fourier transform exists. For the other one, the Fourier transform does not exist. And the answer to this is like this. The imaginary part is j omega, and the real part is sigma, we say. So imaginary is j omega, and this imaginary is also j omega. So an alternative way of drawing the S-plane is actually, the shortcut of it is, this is the sigma axis, and this is the j omega axis. You can also draw it like this, and you put the dashed lines and draw the region of convergence to the right, and for some we will see to the left, etc. But this is where we will draw the region of convergence. This is the alternative S-plane. But look at the name of the vertical axis, it's j omega. Now, for the top red shape here, I said the Fourier transform exists, and for this one, the Fourier transform does not exist, because the region of convergence here includes j omega axis, and j omega means Fourier transform. So when this j omega axis is included in the region of convergence, it means the Fourier transform exists, okay? Congratulations. However, if the j omega axis, this one, is not included in the region of convergence, then it means the Fourier transform essentially does not exist. But the Laplace transform exists. It is still equal to 1 over s plus a, but the region of convergence is here to the right of 2, for example, for this question. And the Fourier transform does not exist because the j omega axis is not included. So it gives us also another solution, deduction, that the Laplace transform is a superset of the Fourier transform. And the Fourier transform is a subset of Laplace transform, only evaluated at j omega. So if you only evaluate the Laplace transform at this axis, at the j omega axis, that would correspond to the Fourier transform. But of course, you can only do that if this axis, the j omega axis, is included in the region of convergence. If it is not included in the region of convergence, then no, it means you simply don't have the Fourier transform. Okay, now here is another question, which is giving us a surprise, and it also indicates the necessity of the region of convergence. Until now, it's necessary because I say so. You have to tell me the region of convergence, I said. But without telling me the region of convergence, it's actually not complete. Now you will understand from this example, the second example. And this example is x of t is equal to minus e to the minus at u of minus t. It's just a signal, but it has a u of minus t, so it's not extending to the right side. On the t-axis, it is extending to the left-hand side. And for a to be, this time if a is positive, then it will be a growing exponential towards the left-hand side. And if a is negative, it will be a decaying exponential towards the right, towards the left-hand side. Of course, towards the right-hand side, it will be a growing exponential. So it depends on which side you're looking at. And since it is u of minus t, we are looking at the left-hand side. So growing exponentials at the left-hand side are essentially decaying exponentials towards the left. Okay, whatever. Let's find the Laplace transform of this one. X of s is equal to minus, because there's a minus sign in the expression of x of t, from minus infinity to infinity, e to the minus at u of minus, ooh, what's going on? U of minus t, and times e to the minus st dt, of course, for the Laplace transform formula. And that would make from minus infinity to 0 because of u of minus t. U of minus t is valid only between minus infinity and 0. And there is a negation still. E to the minus s plus a t. I don't know why these are happening. dt. This is the compact expression. And when you evaluate this, including the negative sign and considering that it is from minus infinity to 0, so there is a further change of orders in the integral, definite integral evaluation, this answer will be equal to 1 over s plus a. You can do it and find this. But we have a problem, right? Look at this, 1 over s plus a and 1 over s plus a. They are the same. So the Laplace transform of this e to the minus atu of t and this minus e to the minus at u of minus t, another signal, clearly a different signal, their Laplace transforms are the same. That is where we need to resolve. And the only way to resolve this concern is by indicating the region of convergence. The top ones and this one's region of convergences are different. Here, this integral converges for the real part of S, this time less than minus a. In the previous case, the integral was converging for the real part of S greater than minus a. This time, real part of a plus S must be less than 0. It must be an increasing exponential as t increases, but since t is between minus infinity and 0, it decreases towards the left-hand side. So that's what we're looking for. We're looking for an increasing exponential for a converging integral for this integral. So real part of S is less than minus a means, or sigma is less than minus a, in other words. If a is, for example, a is equal to 2, okay, minus a will be minus 2. By the way, this is the sigma axis, this is the j omega axis. You can also write it like that, or you could say the real axis and the imaginary axis. We can use it interchangeably, whichever is appropriate. I will just call it like that. And real part of S less than minus a is therefore this part, which is the region of convergence. If you want to write it in expressions, mathematical expressions, you write it like this region of convergence is real part of S is less than minus 2. You can write it like this. So if A is 2, now e to the minus 2t, what does it look like? What does e to the minus 2t look like? So x of t is equal to e to the minus 2t, because a is minus 2. It will be like this, okay, and increasing exponential. But the signal is not e to the minus 2t, it is minus e to the minus 2t times u of minus t. So first, I'm going to say this is x of t is equal to minus e to the minus 2t u of minus t. First, I will negate it. Okay, make it minus. And then I will crop it from here and look at everything to the left-hand side. I'm not going to look at t extending to plus infinity, but it's extending to minus infinity. So this region between minus infinity and 0. And as you see in this region, when a is equal to 2, I'm sorry, a is equal to, yeah, a is equal to 2, it is in a convergent state. And I'm just messing up with minuses and pluses because when a is equal to 2, minus 2 is here, and to the left of minus a does not include the j omega axis. So I'm confused about why this happened to be like that. I will have to correct this. I may want to check if this here, it is a plus a or a minus a. According to my notes, it's minus a, but I'm not very much sure about that. But I can at least explain the situation in the region of convergence domain, which is the universal result that you will be always having. If the region of convergence, for this one, for instance, it seems to not contain the j omega axis, and if j omega axis is not included, by the way, e to the minus 2t is not like this. Excuse me. Now I realized my mistake that I made. So let me erase it. I'm sorry about this. E to the minus 2t is a decaying exponential. Why am I drawing it like an increasing exponential? Excuse me about that. E to the minus 2t is a decaying exponential like this. Okay? And minus of e to the minus 2t times u of minus t will be this. Okay, it will look like this, which is not a convergent place, is divergent, let me say. So the Fourier transform does not exist. Okay, now we are doing it. The Fourier transform does not exist is also visible from this region of convergence with the same rule. Why does the Fourier transform not exist for a is equal to 2 case? Because the j omega axis is not in the region of convergence. However, if we continue with the same example and say that a is equal to, this is sigma, this is j omega, a is equal to minus 2, then minus a will be here, which is 2. And the real part of s less than minus a will correspond to this place as the region of convergence. And it will mean that our signal is x of t is equal to minus e to the minus 2, which is 2t u of minus t, this signal. Now this signal is an increasing exponential like this. E to the 2t is like this, and negative of it will be like this, okay, and it will stop at t is equal to 0, extending from minus infinity to 0. So this is a convergent signal, and the Fourier transform exists. Using the Dirichlet conditions, the Fourier transform exists. And we can also see that the Fourier transform exists from the region of convergence because this j omega axis is included in the region of convergence. Now the next question that we will talk about is about what is the inverse Laplace transform then? We have a Laplace transform if we have a Laplace transform of x of s. Let's say it's equal to 1 over s plus a. Then what is x of t, which is the inverse Laplace transform of x of s? X of s is the Laplace transform of x of t. So what is x of t? Now we have two options, unfortunately. If you are given only this much information, the inverse Laplace transform of 1 over s plus a is either e to the minus at u of t or minus e to the minus at u of minus t. It can be either of them, and you don't know if only this much information is given to you. So you need further information plus region of convergence. The region of convergence must be given to you. And there are two alternatives of the region of convergence. It's either real part of s is greater than minus a, or real part of s is less than minus a. Why are these the only options that you have for this Laplace transform? We will soon discover that one too. I'm just gonna tell you this. If you know the regions of convergences, then you will decide the inverse Laplace transform. As you see, the inverse Laplace transform here, we didn't use any integrals or anything, which is kind of okay because we shouldn't use them. These integrals are complex valued integrals, and from complex calculus, you may remember how to evaluate those integrals of the Laplace transform. I will still write down the formula, by the way, to be on the strict side or the rigorous side, the formula, the exact formula of the inverse Laplace transform, but you will notice that it's not something that you know how to evaluate from simple first year calculus. It's something else. And in fact, the way to do it is by knowing the inverse Laplace transform, okay? And if the region of convergence is a real part of S is greater than minus A, then you have to give me this answer as x of t. And if the region of convergence is given as real part of S is less than minus A, then you have to give me this answer. The answer is, the time signal is minus e to the minus at u of minus t. So there are two options, and the options are separated or decided according to the region of convergence and nothing else. Now, let us see how these options of real part of S is greater than something, let's say gamma, or real part of S less than gamma, another number, or real part of S is less than alpha but greater than beta. This is also possible. And there is a fourth option where real part of S, or we cannot really write it like this. Let's write it like this. We write it as region of convergence is an empty set. There is no place where the integral converges. This is, of course, a pathetic result. Region of convergence is an empty set. It means that even the Laplace transform does not exist. Usually, the Laplace transform exists for some sigma values, but if you cannot find any sigma value for which the integral converges, then it means the region of convergence is an empty set, and it literally means the Laplace transform does not exist. But the others are real part of S is greater than something or less than something, or less than something and greater than some other thing, which is in between two values. How do we decide on these? How do we find the regions of convergences? We have found the regions of convergences for the first two examples by looking at how the integral converges, for which range of real part of S, for which range of sigma values do we have a convergent integral, but we cannot do it every time. Sometimes the integrations will be too complicated and we cannot really deduce what is the condition of the convergence of this very complicated integral. But there is an easy way to check the region of convergence. Easy check of region of convergence. This easy check is like this. You look at x of S, okay, and you look at the denominator of this x of S. Let's say it is S plus A, and in the numerator, let's say we have something else. But the denominator is S plus A. We are going to talk about a terminology which is called the pole. Is a point where x of S diverges to infinity. Okay, it goes to infinity. And if in the denominator we have s plus a like this, when does x of s go to infinity? It goes to infinity when s is equal to minus a. So the pole is at s is equal to minus a. At s is equal to minus a, we have a pole. And on the s-plane, this is the s-plane, sigma j omega, let's say, s is equal to a is marked. We mark it with a cross. Let's say a is a real number, so s is equal to minus a. Let's also assume that it's positive. S is equal to minus a. You put a cross at that point, and that indicates the pole. How do we find the pole? By looking at the roots of the denominator. Here we have a single order polynomial of s, therefore we have one pole only, and it's at s is equal to minus a. We put a cross, and we put a dashed line that crosses the pole vertically. Because j omega, the value of j omega does not change the convergence. It has nothing to do with the convergence. Only the real part is indicating whether it's converging or not. So there's a pole at minus a, so we put a dashed line. Now the region of convergence is either to the right. The right, let me indicate by this orange region of convergence, where sigma is greater than minus a. And the other alternative is the light green region of convergence here. I am, well, this is quite invisible. Excuse me about that. I'm going to delete and write it with a darker color. The region of convergence is sigma is less than minus a. Okay, so two options, less than minus a or greater than minus a. How do we decide? We decide according to the extent of the signal. What do we mean by that? It's, for instance, if it is something times u of t, extent is towards plus infinity. It is right-hand sided. For example, e to the minus at u of t is a right-hand sided signal. It starts from 0 and extends to the positive side. So the region of convergence is also right-hand sided. It is the orange one. So the signal is right-hand sided. And the region of convergence is also right-hand sided. For instance, for this one, it means the signal is actually probably, if it is 1 over s plus a, then the signal is e to the minus at u of t. This is the right-hand sided solution. If the region of convergence is to the left of the pole, like the green one, then the signal is the left-hand sided solution. So correspondingly, x of t is, if it is 1 over s plus a, if x of s is 1 over s plus a, so maybe I should write it that way, then x of t is minus e to the minus at u of minus t. So we decide on the region of convergence according to the right-hand sided or left-hand sidedness of the signal. So the signal is left-hand sided. And overall, I was assuming that it is 1 over s plus a. So if the signal is right-hand sided, the region of convergence is also right-hand sided. If the signal is left-hand sided, the region of convergence is also left-hand sided. Where is the region of convergence boundary? The boundary is along the pole. The pole is the root of the denominator. It's the place where the denominator becomes 0. So if it is 1 over s plus a, the root is The root of s plus a is minus a, so the pole is at s is equal to minus a. We may have various other ways to look at it, but as a result of it, if x of s is equal to, so this is the rule that we will elaborate further in the upcoming lectures. If x of s is equal to the numerator of s over the denominator of s, then the poles are at the roots of denominator of s. How many roots do we have? It depends on the order of the denominator polynomial. If it is second order, for example, it means we have two poles. Those poles, one of them may be at A, the other one may be at B. And the time domain signal corresponding to these will be determined according to whether it's to the right-hand side or the left-hand side of each individual pole that we will have. We will continue with the second order example that will be better explaining how to proceed with these things. But poles are important. Soon we will also come up with the roots of the numerator polynomial, n of s here, which we will call them zeros, of course, because when n of s is 0, then xs is 0. When ds is 0, xs is infinity. Those are the poles. When ns is equal to 0, those are the zeros. We will put both the poles and the zeros on the Laplace plane, locating those points and indicating them with crosses and small circles for zeros will be the critical issue, and most of the questions that you will encounter will require accurately drawing these poles and zeros, locating them, and indicating what is the region of convergence to the right-hand side of this, to the left-hand side of this, etc. But we will see all of these with plain examples. Until now, we have seen only one example to the right, one example to the left. We will continue with these, of course, on Wednesday. So we can stop at this point. If you have any questions, you may ask, but I'm sure most of those questions will be answered on Wednesday in the next lecture. We will continue with the Laplace transforms. They are not very difficult. As you see, they are very logical, and students mostly understand these topics pretty well, and they perform pretty well in Laplace transform questions. So you are pretty much safe, as opposed to the complicated convolution and Fourier transform questions, which are unfortunately somehow found to be more difficult by the students. Okay. Any questions, as I said, but no questions were arrived. So if no further questions, I will end the meeting, end the recording and end the meeting. And let's meet on Wednesday at the same place, the same hour. Not the same hour, of course, afternoon. All right, see you on Wednesday.